Welcome to this detailed learning series on bar bending schedule, or BBS, a must-know topic for every civil engineer and site supervisor. Here's what you'll learn in this course, broken down chapter by chapter. Book Chapter 1. Introduction to RCC Construction. Basics of RCC. Importance of Steel Reinforcement. Book Chapter 2. Understanding bar bending schedule. What is BBS? Why is it essential in construction projects? Book Chapter 3. Materials and Tools. Types of steel reinforcements. Bar bending tools and equipment. Steel properties. Quality control at site. Book Chapter 4. Preparation of bar bending schedule. Step-by-step process to prepare a BBS. Book Chapter 5. Reinforcement detailing in structural elements. Foundation, column, beam, slab. Book Chapter 6. Detailed examples. Sample BBS for footings, columns, beams, and slabs, all explained practically. Whether you're a student, site engineer, or preparing for interviews, this course is your complete guide to mastering BBS. Let's begin the journey. Chapter 1. Introduction to RCC Construction. What is RCC? RCC stands for Reinforced Cement Concrete. It is a mix of concrete and steel bars. Concrete is strong in compression but weak in tension. Steel is strong in tension. So, when we combine both, we get a strong material that can handle all kinds of loads. That's why RCC is used in buildings, bridges, dams, and many other structures. Why is it called reinforced? The steel bars inside concrete are called reinforcements. The word reinforcement means adding strength, just like backup in the army or police. It also controls cracks due to shrinkage and temperature changes. Weight of RCC. The weight of RCC is about 25,000 newtons per cubic meter. Main components of RCC. Concrete. A mixture of cement plus sand plus aggregates plus water. Gives compressive strength and forms the base of the structure. Steel reinforcement, rebars, provides tensile strength and helps concrete bend without breaking. Advantages of RCC. Strong and durable. Can be used in many types of structures. Fire and weather resistant. Cost-effective for small and large projects. Why is steel reinforcement important? Concrete can't handle pulling or tension forces on its own. Steel absorbs these tensile forces. It helps spread the load evenly. It improves the safety and strength of the entire structure. Why steel is used in RCC? Steel is strong in tension, pulling force. It is elastic, bends but returns to shape. It bonds well with concrete because both expand equally with heat. Steel is easily available in India. What steel does in RCC? Gives tensile strength to concrete. Reduces cracks. Keeps the structure stable and safe. Helps in creative and complex designs. Did you know? Common steel bar sizes, 8, 10, 12, 16, 20, 25, 28, 32.
Chapter 2. What is bar bending schedule, BBS? BBS is a list of steel bars used in a construction project. It shows type, size, length, number, and shape of each bar. Helps in cutting, bending, and placing the bars correctly as per drawing. Why BBS is important. Gives a clear plan for steel work. Helps in accurate cutting of bars. Reduces steel wastage. Makes bar placement faster and easier. Useful for budgeting and cost control. Benefits of using BBS. Fewer mistakes during steel cutting. Saves time, money, and materials. Speeds up site work. Better quality and easy inspection. Avoids delays and rework.
Chapter 3. Role of steel in RCC. Concrete is strong in compression but weak in tension. Steel reinforcement gives concrete the tensile strength it needs. Good qualities of steel. Strong in tension. Can bend without breaking, ductile, bonds well with concrete. Long-lasting, durable, easy to cut, bend, and fix. Expands like concrete when heated. Types of steel, mild steel bars, smooth-surfaced plain bars. Used in small projects and earthquake zones. More flexible due to low carbon. Strength. Up to 250 N per square millimeter. Drawback. May bend too much during earthquakes, causing cracks. CTD bars, or cold twisted deformed bars, are made by twisting plain bars when they're cold. This gives them higher strength, but also makes them less ductile, or less bendable. The twisted ridges give a better grip with concrete. They can bend, but not as well as TMT bars. Now, let's talk about TMT bars, thermomechanically treated bars. These bars have a tough outer layer and a soft core inside. This gives them great strength, flexibility, and corrosion resistance. They are the preferred choice for earthquake-resistant buildings. TMT bars are stronger than mild steel and CTD bars. You'll find them in grades like FE 415, FE 500, and FE 550. The higher the number, the stronger the bar. They also offer excellent bending and rebending ability. So in short, CTD bars are strong, but TMT bars are stronger, safer, and smarter. Let's talk about corrosion-resistant bars, special steel used to fight rust in tough environments. CRS bars are an advanced type of TMT bars. They contain copper, chromium, and phosphorus to resist corrosion better. Important tip: never store steel bars directly on the ground. Keep them covered and away from rust, oil, and grease. Did you know? Epoxy-coated bars. These bars are coated with epoxy to protect against rust. Best for marine areas, bridges, and coastal zones. Galvanized bars. These bars are coated with zinc. Great for wet and corrosive environments. So, for long-lasting structures, use the right type of corrosion-resistant bars. Let's break down common steel grades used in construction. Fe 250. Fe means iron, and 250 is the yield strength 250 MPa. Used in low-stress work, like small homes or simple structures. Fe 415. Stronger than Fe 250, with 415 MPa yield strength. Used in residential and commercial buildings. Fe 500. Even stronger, 500 MPa yield strength. Perfect for bridges, high-rises, and heavy structures. Fe 500D. D stands for ductile, it bends more before breaking. Same 500 MPa strength, but better for earthquake zones. Choose the right Fe grade based on your project's strength and safety needs. Let's look at the basic tools used for cutting and bending steel bars on site. Cutting tools. Hacksaws and bandsaws are used for cutting smaller bars. For bigger bars, we use electric or hydraulic rebar cutters, fast and accurate. Bending tools. Hand benders are used for small bars. They're simple and great for quick bends on site. Using the right tool means better accuracy and safer construction. Here are more essential tools used in steel reinforcement work: bar bending machines. Automatic machines that bend bars to exact angles, fast and accurate. Measuring tools. Tape measures and rulers for correct bar lengths. Chalk and markers help mark where to cut or bend. Handling tools. Cranes and hoists lift heavy steel bars safely. Rebar tying tools tie bars together using binding wire, manually or automatically. Right tools equals better speed, accuracy, and safety on site.
Let's quickly understand why the properties of steel are so important in RCC construction. Tensile strength. How much pull the steel can handle without breaking. More strength equals safer structure. Yield strength. The point where steel starts to bend permanently. High yield strength equals strong and stable building. Ductility. Steel's ability to stretch without breaking. Essential during earthquakes. Bonding ability. Steel must stick well to concrete. Good bond equals smooth load transfer, no slippage. Small diamond corrosion resistance. Helps steel last longer, even in wet or coastal areas. Checkmark. Now let's talk quality control. Tensile test checks strength. Bend test checks flexibility. Bond test checks grip with concrete. Good steel equals strong, safe RCC structures. Chapter 6. Are you confused about how to calculate cutting lengths for bent bars? Don't worry. In this video, I'll explain the cutting length of reinforcement bars for 3 commonly used shapes, with proper bend deductions. Let's go step by step. Shape 1: straight bar. This is the simplest case. A straight bar with no bends or hooks. Cutting length equals L, where L is the full length of the bar. No bend means no deductions required. Just measure the bar from end to end. Example, if L equals 2 meters, cutting length equals 2 meters. Simple. Shape 2L bend bar, 90 degrees bent bar. This is a bar bent at 90 degrees, forming an L shape. To calculate cutting length here, we use the formula. Cutting length equals A plus B, bend deduction. Why the deduction? When we bend a steel bar, the length required to form the bend is slightly shorter than the straight length. This is because bending compresses the inner side of the bar and stretches the outer side. Standard bend deduction for 90 degrees equals 1 times d, where d is the diameter of the bar. Formula becomes cutting length equals a plus b1d. Example, a equals 50 centimeters, b equals 40 centimeters, bar dia, d, equals 12 millimeters. Cutting length equals 50 plus 40 to 1 times 1.2 equals 90 minus 1.2 equals 88.8 centimeters. Shape 3 cranked bar or Z-shaped bar, 130 to 230. This shape has two 90 degrees bends, forming a crank or Z shape, commonly used in slab reinforcement. Cutting length equals a plus 2b, bend deductions. Since there are two 90 degrees bends, deduction equals 2 times d. Formula becomes cutting length equals a plus 2b 2d. Hammer and wrench example, a equals 100 centimeters, b equals 30 centimeters, bar dia equals 10 millimeters. Cutting length equals 100 plus 2 times 30, 2 times 1.0, equals 100 plus 60 minus 2 equals 158 centimeters. Shape 4 cutting length explanation. Shape 4 consists of three legs, typically labeled A, B, and C, connected with two 90-degree bends. It's commonly used in beam or column detailing. To calculate the cutting length, you first add all three leg lengths, A, B, and C, but since there are two bends, you need to subtract the material that gets overlapped due to bending. Every 90-degree bend requires a standard deduction of 1 bar diameter, 1d, from the total length, as the bent portion consumes less length than a straight one. So for two 90 degrees bends, the total bend deduction becomes 2d. Final cutting length formula. Cutting length equals a plus b plus c 2d. This ensures the steel bar is cut precisely to the length needed on site. Shape 5 cutting length explanation. Shape 5 also has three legs, A, B, and C, with two 90-degree bends, although the overall shape might differ from shape 4. Despite the change in geometry, the logic for cutting length remains the same. You sum up the straight portions, A plus B plus C, and then subtract 2 times the bar diameter for the two 90 degrees bends. Final cutting length formula. Cutting length equals A plus B plus C 2d. So whether it's shape 4 or shape 5, the principle of bend deduction remains consistent. Shape 6 cutting length and bend deduction explanation. Shape 6 consists of four linear segments labeled A, B, C, and D, with a total of 3 bends, 2 of 45 degrees and 1 of 90 degrees. To find the total cutting length, we begin by adding all the straight segments. Cutting length, before deduction, equals A plus B plus C plus D. Now, we must account for the bend deductions, because bending the bar causes it to take up slightly less length compared to if it were laid straight. Here's how deductions are applied. For each 45 degrees bend, we subtract 0.3 times the diameter of the bar, 0.3d. For each 90 degrees bend, we subtract 1 times the diameter of the bar, 1d. Since shape 6 has two bends of 45 degrees equals 2 times 0.3d equals 0.6d. One bend of 90 degrees equals 1 times 1d equals 1d. Total bend deduction equals 0.6d plus 1d equals 1.6d. So the final formula becomes cutting length equals A plus B plus C plus D 1.6d. This adjusted length ensures the bar is fabricated precisely to match design specifications, considering the material loss due to bending. Shape 7 cutting length and bend deduction explanation. 130 to 215, shape 7 typically includes 3 linear segments, A, B, and C, with 2 bends, each at 45 degrees. We start by adding the straight lengths. Cutting length, before deduction, equals A plus B plus C. Since this shape includes 2 bends of 45 degrees, we apply the standard deduction of 0.3d per 45 degrees bend. Total bend deduction equals 2 times 0.3d equals 0.6d. So the final formula is cutting length equals A plus B plus C 0.6d. By applying these deductions correctly, we reduce errors and avoid material wastage during cutting and bending. Shape 8 rectangular stirrups with 5 bends. Shape 8 stirrup is a rectangular stirrup with 3 bends of 90 degrees and 2 bends of 135 degrees, typically used for beam or column reinforcement. Cutting length formula. Cutting length, CL, equals 2A plus 2B plus 2 times hook length minus bend deductions. Where A equals clear horizontal length of stirrup, B equals clear vertical length of stirrup. Hook length equals as per is 2502, standard hook equals 10D, D equals bar diameter, bend deduction equals reduction in length due to bending of the bar. Bend deductions breakdown. 3 bends at 90 degrees equals 3 times 2D. 2 bends at 135 degrees equals 2 times 3D. Total bend deduction equals 3 times 2D, plus 2 times 3D, equals 6D plus 6D equals 12D. Final formula. CL equals 2A plus 2B plus 2 times 10D minus 12D. This gives us the total straight length of bar required before bending into shape 8. Shape 9 refers to a circular stirrup, typically used in circular columns or piers. It forms a closed ring with 2 hooks. Cutting length formula. Cutting length, CL, equals pi times D plus 2 times hook length minus bend deductions. Where D equals inside diameter of circular stirrup pi times D, and D equals circumference of the circle. Hook length equals 10D, standard, per hook, bend deductions equals for 2 hooks bent at 135 degrees. Bend deductions breakdown. Each 135 degrees bend equals 3D deduction. 2 bends equals 2 times 3D equals 6D. Final formula. CL equals pi D plus 2 times 10D minus 6D. Or in simpler terms, CL equals pi D plus 20D minus 6D equals pi D plus 14D. Shape 10 chair bar. A chair bar is used in footings and slabs to maintain spacing between top and bottom reinforcement. Cutting length formula. Cutting length equals head of chair plus 2 times height of chair plus 2 times leg of chair minus bend deduction. Bend deduction equals 4 bends of 90 degrees equals 4 times 2D equals 8D. Step by step. Height of chair equals total depth of footing minus 2 times clear cover minus diameter of bottom main bar minus diameter of top main bar plus distribution bar head of chair equals 2 times spacing of top distribution bars plus 2 times 50 mm leg of chair equals 2 times spacing of bottom main bars plus 50 mm. Final formula. CL equals head plus 2 times height plus 2 times leg minus 8D. Note, D is the diameter of the chair bar used. Shape 11 irregular stirrup. This stirrup is non-standard and may follow a trapezoidal or polygonal shape, used in special beam or column cases. Cutting length formula. Cutting length equals A plus B plus C plus D minus bend deductions. Bend deductions equals 3 bends of 90 degrees equals 3 times 2D equals 6D. Final formula. CL equals A plus B plus C plus D minus 6D. Shape 12. Cutting length of stirrup. Cutting length equals A plus B plus C plus D plus E. Bend deduction equals A plus B plus C plus D plus E for bend of 90 degrees. Shape 13. Cutting length of stirrup. Cutting length equals A plus B plus C plus D. Bend deduction equals A plus B plus C plus D 3 bend of 90 degrees. Shape 14. Cutting length of stirrup. Cutting length equals A plus B plus C plus D. Bend deduction equals A plus B plus C plus D 4 bend of 90 degrees.
Thank you so much for your patience and attention throughout this session. I truly hope you now have a clear understanding of the bar bending schedule concepts we discussed. To help you practice and build confidence, I've included a set of problems at the end of this video. I've also shown the answers alongside, so once you try solving them on your own, verify your solutions and understand where you can improve. Remember, the only way to master BBS is through practice and repetition. You've got this, just stay consistent and keep learning.